What is this week's syllabus? Torque. Uh, Torque already we have defined. Torque equation, moment of inertia, basically. So now I will start defining moment of inertia. See, remember, moment of inertia is analogous to mass in translational motion. Mass in translational motion. Right. Just confirm whether my voice is audible or not now. Dakshesh. Dakshesh, I didn't took class yesterday. I had a meeting at central office. This is the first class of this week. Just confirm, ECL. Someone post me comment. Moment of inertia is analogous to mass in translational motion. So what exactly is moment of inertia? Now you take some rigid body. And remember, when I am defining moment of inertia, I need to define with respect to some axis. I am assuming this is my axis. And these are different particles. M1, M2, M3, M4, M5, Mn, and so on. So Mn. Mn is at a perpendicular distance of R1. This is at a perpendicular distance of, perpendicular means with respect to the axis. And M3, R3, M4, R4, M5, R5, Mn, Rn. N particle system. So the moment of inertia of this system is sigma I mi Ra square, which means M1 R1 square plus M2 R2 square plus so on Mn Rn square. This is the definition of moment of inertia. This is how it is defined. So in translational motion, you don't require distribution, just require what amount of, what quantity of mass it is. Today's class is completely basic. Again, I will take between 4 to 5. Come here and sit. I'll take it from ECL. I'll continue the class today. Right. Now, this is what we will define as, so moment of inertia depends on one, distribution of the mass about the axis, and not only that, selection of axis of rotation. Sometimes, how we use center of mass concept, we use a similar concept in this. Now, if the entire rigid body is replaced with one single point mass, M, and this is the same axis. And this is some K. Now, only one point mass, or you can choose in way, sometimes we can take it as a ring, no issues. The entire mass distributed on the surface, on the edge of the ring. In this case, only for this point mass, what is the moment of inertia? Simply mk square. Now remember, if mk square is equal to m1 r1 square plus m2 r2 square plus so on mn rn square, such a k is called, where m is equal to sigma I mi. Such a k is called radius of gyration. That is called radius of gyration. Okay. So in some cases, I will represent radius of gyration instead of total moment of inertia. Some cases, right? Next, one more important point is moment of inertia is a scalar quantity. Actually, tensor quantity. But if I say tensor, you might get some tension like kind of thing. That is the reason why I'm just avoiding this. Moment of inertia gives some information about distribution about the axis. That's the basic idea about moment of inertia. So wherever mass I used in translational motion, I will use moment of inertia in rotational motion. Right. See, it is as same as you release a object on a smooth horizontal floor. It keeps on moving. And that property you said inertia of motion. Similarly, for example, under ideal condition, you switch off the fan. If there is a vacuum and there is no air, then what happens? The moment you switch off, it keeps on rotating because there is no loss of energy there. Why it is not coming to rest by itself? It is because of moment of inertia of this system. The property there we defined as moment of inertia. In translational motion, I said mass of the body is a measure of inertia, whereas in rotational motion, and what way I define moment of inertia? So I need to follow some methodology. That methodology is this. So this is the introduction to moment of inertia, right? Now we have different ways of identifying the distribution, but basically what I would like to do is before you start the moment of inertia, you need to know two theorems. Okay, one is parallel axis theorem. One is a parallel axis theorem. See, in a parallel axis theorem, what the statement provides us is, you imagine that this is some rigid body. This is some rigid body. What is a rigid body? Basically, in a motion, during the course of motion, the distance between the particles with respect to body do not change. Cycle chain is not a rigid body. A rod is a rigid body. Why cycle chain is not a rigid body? The distance between links might change in the course of motion, depending upon the way how you are moving that. Got the point? Whereas in case of a rigid rod, no such situation exists. This is a rigid body. I am choosing that this is the center of mass of the system. And this is some random point A. And imagine an axis that passes through A. And this distance is D. This distance is D. Now you have some random point P. There is some random point P. Now, what moment of inertia or what exactly the parallel axis theorem defines is I know the moment of inertia about this axis, ICM. And I want to find moment of inertia about this axis. And these two are parallel axes passing through the point. And the distance between the two parallel axes is d. Then parallel axis theorem defines that I is equal to ICM plus total mass times d square. This is the statement of parallel axis theorem. Right. Let us try to understand. Let us take point C as origin 0, comma 0, comma 0. Then what is going to be the coordinates of A? T, comma 0, comma 0. Now imagine a plane. Imagine a plane. Right. So this point is Q and this point is some R. Right. Imagine the plane PQR is above the plane that contains CA. And the coordinates of Q are simply the coordinates of Q are simply 0, comma 0, comma Z. What about the coordinates of R? The coordinates of R are simply D, comma 0, comma Z. Okay, the area x-axis is right side, y-axis is towards you, top direction is z-axis. What about the coordinates of point P? We will call the coordinates of point P as x1, y1, z1. Okay. Now, do you have any doubt in the geometry? Remember, I want to find the moment of inertia about an axis passing through A or about the axis passing through A or otherwise. Right. Forget about the theorem. How to find the moment of inertia of this element? Simple. This particular element will have a moment of inertia given by sigma I, mi. What is the perpendicular distance? PR. PR is the perpendicular distance. PR square. Right. Can you please help me in writing PR in the coordinates which I have given to you? This is nothing but sigma I, mi. Can you please help me in writing PR? Are simple. The coordinates are, the x coordinate is x1. From this, the x coordinate is x1 minus d distance. Next point, yi minus 0. Next point, zi, in fact, with respect to this, both are in the same z coordinate. So zi minus zi square. Right. So this is nothing but sigma I mi x1 square plus xi square plus d square minus 2xid plus yi square plus 0. This is nothing but sigma I mi xi square yi square minus 2xi d plus d square. Just please give me a clarity that do you have any doubt till this step? Now here lies some problems for me. See, please try to understand. Can you please tell me what is sigma I mi xi? Moments. Sigma I xi. Moments about center of mass. Because xi is defined with respect to c. Similarly, we will have one more observation. This is all about moments about the center of mass. Actually, you should write this same as because center of mass is fixed here, right? So therefore, the moments about center of mass is equal to 0. We know this as per the characteristics of center of mass. Now just tell me, do you have any doubt till this point? Now, what is finally that I could write is moment of inertia about what is this axis? What is this axis? AB. Moment of inertia about AB is finally sigma I. We will make a note thereafter later. No issues. Right. Right. Later on, I'll write. Now we need to prove this is equal to this plus this. I'll do it. No issues. Already, this can be written as sigma I mi xi square plus yi square minus 2d times sigma I mi xi plus sigma I mi d square. So therefore, I can be written as అలా ఉంచండి చెప్తాను నేను సిగ్మా ఐ ఎంఐ ఎక్స్ఐ స్క్వేర్ ప్లస్ వైఐ స్క్వేర్ minus 0. Why? Just now I have proved this is 0. Plus sigma I mi times d square. Abhaya, try to please understand. You got this part already here. You got already this part. So I need to prove that ICM is nothing but this. So therefore, moment of inertia about CQ. How you will write moment of inertia about CQ? This is nothing but sigma I mi pq square. This is nothing but sigma I mi, anyone in the class. Xi minus 0 square plus yi minus 0 square plus zi minus zi square. And this is nothing but, by the way, sigma I mi xi square plus yi square. You will call this as ICM. Let this be equation 2 and let this be equation 1. What have I proved? From 1 and 2, we can write, I is equal to ICM plus M T square. This is the proof for, hence the proof, hence proved. This is the expression for parallel axis theorem. See, you don't require derivation actually. You need to remember this. But someday you will question me how you got this. That is the reason why I have derived this thoroughly. Remember, you can apply this theorem for, we can apply this for linear distribution, surface distribution, volume distribution. For a rod, you can apply. For a disc or ring, you can apply. For a volume objects, cone, sphere, cylinder, cube, rectangular box. Tell me whatever you want. You can apply. Parallel axis theorem only. So what is the significance of parallel axis theorem? If I know the moment of inertia about an axis passing through the center of mass, I can give moment of inertia of the same body about any other point, but only condition is parallel to the first axis. It's not like skew vectors. You cannot give like that. Right. So next thing, what we need to learn is perpendicular axis theorem. perpendicular axis theorem. Right. Now the question is, this is applicable only for plane objects. This is strictly applicable for plane objects. Now imagine this is a plane lamina. X-axis, Y-axis. Say this is Z-axis. This is some point O. Through O, all the three axes are passing. Perpendicular axis theorem says that Ix plus Iy is equal to Iz. Remember, Ix and Iy are in the plane of the object, which means about this moment of inertia is Ix, about this moment of inertia is Iy, about this moment of inertia is Iz. So what is Iz? You take one element P. Iz is nothing but sigma I mi op square. Agreed? This is nothing but sigma I mi. This is xi. This is yi. Yes or no? This can further be written as xi square plus mi yi square. What is this in fact? Ix, iy. Hence proved. Simple proof. Okay. See, remember, I will apply these things wherever in appropriate situations. I'll simply apply this wherever the situations are. Next. So I've just introduced what is moment of inertia. I have defined what is parallel axis theorem, and I have defined what is perpendicular axis theorem. Right. Now just give me any confirmation that you have any doubt on this. ECL. I don't. Okay, right. Thank you. Next. Now we will derive some situations of moment of inertia. Okay. So, see, someone please remind me around 9:35, 9:40 till 9:40, I'll define whatever possible and moment of inertia. Thereafter, I will go with defining tau is equal to A alpha. Evening, we should apply it for some question. With theory, 1.5 hour, bus. Application, you can take full year. Right. Next. Now, you try to please see that. You try to please see that. I am deriving moment of inertia of a thin rod. So imagine that you have a thin rod. Here lies the center of mass. So first I will derive about this axis. For this purpose, I'll take an element here, which is at a distance x, length dx. I will define a term called lambda, which is called mass per unit length. Right. This element, the moment of inertia of this small element is nothing but lambda dx mass x square. Agreed or not? What is the total moment of inertia? You will have such elements from minus L by 2 to plus L by 2 di. So this in turn dx into x square minus L by 2 to plus L by 2. This is nothing but lambda by 3. Okay, x cube. Lower limit is a minus L by 2. Upper limit is a plus L by 2. Lambda by 3 L cube by 8 plus L cube by 8. This is nothing but lambda L cube by 12, which is nothing but ml square by 12. Remember, moment of inertia about an axis passing through the center and perpendicular to the length of the rod is this. This is ICM. I am not writing all that nonsense writing here. You know already, you can see that. If you want to find the moment of inertia about this end, okay, let this be I1. So apply parallel axis theorem. Apply parallel axis theorem. By applying parallel axis theorem, I can get I1 is equal to ICM plus M into L by 2 whole square. This is nothing but ml square by 12 plus ml square by 4. Denominator is 12. 4 by 12 ml square, which is nothing but ml square by 3. That is I1. That is I1. That is parallel axis theorem application. You cannot apply perpendicular axis theorem for rod. Why? It's a linear distribution. Only for aerial distribution, area-wise elements, plane objects only you can apply. Next, what if you have a situation like this? What if you have a situation where the rod is like this and the axis is like this, which makes an angle theta. Now you take some r and an element dr. So for this, the moment of inertia of that small element is lambda dr. Everything is the same. But instead, perpendicular distance become r sine theta. This distance becomes r sine theta. So therefore, r sine theta. Here I am using the basics only. Mass perpendicular distance square. So the total moment of inertia is lambda r cube sin square theta dr. So lambda r square, sorry, r square. Okay, you will get it as lambda r cube by 3 sin square theta. Remember, you will have r from minus L by 2 to plus L by 2. Arya, trust me, you will get it as ml square by 12 sin square theta. So these are three prominent axes that you must have an idea. Now, just do you have any doubt on this? Do you have any doubt on this, students? Right, I am first deriving the basic ECL students. Give me confirmation. Right, thank you. Next. Now, see, I'm just deriving basics only. Basics. Thereafter, we will start applying first basics. The moment of inertia of a thin ring. Thin ring. Now imagine a thin ring-like kind of structure over here. And this is axis of a ring. D theta. So try to please understand what is the mass part of this. Simple. If the total mass is m by 2 pi times d theta. That is mass of the element. Right. So now what is the moment of inertia of that element? M by 2 pi d theta mass distance square. Any doubt? See, what will trouble you? I'll explain. You may compromise here. ఏదో రాశారులే అలా గుర్తుపెట్టుకోలేమో అని తప్పు ఎగ్జామ్లో రాదు మీకు వర్కౌట్ కాదు మీకు ఇది క్లారిటీ ఉందా క్లియరా క్లాస్లో ఉన్న అందరూ షూర్ రైట్ నా ఇప్పుడు మొమెంట్ ఆఫ్ ఇనర్షియా డిఐ పార్ట్ ఈజ్ ఈక్వల్ టు mr square by 2 pi times 2 pi. Now you have parallel axis theorem. Now you have a clear idea about. Try to see what I am doing is I am first finding moment of inertia about an axis passing through its center of mass. Now this is ICM. Now what if I question you about an axis passing through here? Let this be I1. Then your answer will be I1 is equal to ICM plus MR square. So this will become 2MR square. What if I choose another axis like this? It's a diameter passing through the center. Let this be ICM dash. How to find? Simple. Now see, please try to understand when you are seeing this part, you can also imagine another axis like this, which is a 90 degrees. Let this be Ix. Let this be Iy. But don't forget, Ix or Iy are similar axes. They are similar axes. And this is ICM dash. So therefore, ICM is Ix plus Iy, which is 2 ICM dash. Therefore, ICM dash is equal to ICM by 2, which is nothing but MR square by 2. Now you know ICM dash. You can find about this axis now. Let this be I2. Okay, what is I2? I2 is parallel axis theorem again. What I have applied here? I have applied perpendicular axis theorem. What I have applied here is parallel axis theorem. So what is I2? I2 is nothing but ICM dash plus MR square, which is MR square by 2 plus MR square, which is nothing but 3 by 2 MR square. So now tell me, do you have any doubt in this? So overall, this is the expression for moment of inertia of a thin ring. Confirmation from ECL required. Confirmation from ECL. Clear, sir. Thank you. Right. Now I am going to do the moment of inertia of a thin circular disc. So I am just discussing basic cases only today. All complicated cases I'll discuss tomorrow. Right. Now you have a circular disc like this. Right. You can imagine that this is some circular disc. Now here is the axis that passes through the center. And let the moment of inertia be ICL. I am defining a new term now, sigma, not lambda. Why? See, this is an aerial term. The previous one is a linear terms. Sigma is mass per unit area, which is nothing but capital M by R square. Now, in this also, we imagine a ring type structure. See, the radius is R and the width is dr. Agreed? I am taking an elemental ring. Let us take an elemental ring. Okay, what is the mass of this ring? Sigma times 2 pi r dr. That is the mass of the ring. So what is the moment of inertia of this arrangement? dm times r square. 2 pi sigma r square dr. That is a di. Now do the integration part. The moment of inertia of this part is 2 pi sigma 0 to capital R. Remember, this is ICM. Don't forget that. And you will get R square dr 0 to capital R. Or no, why R cube? 1 minute. 2 pi R dr R cube, right? R cube, R cube. Good. This will become 2 pi sigma r power 4 by 4. I will modify this like this. Sigma pi r square part into r square part by 2. Have you identified what is the sigma pi r square? Mass. That's the mass of the disk. mr square by 2. So therefore, moment of inertia of this disk about an axis passing through the center perpendicular to the plane of the disk is mr square by 2. Now the question is, if I imagine another parallel axis and if it is I1, clearly I1 is equal to ICM plus mr square. This will become 3 by 2 mr square. Now you imagine a diametric axis now. This is the diametric axis ICM dash. How the way you have applied perpendicular axis theorem? Apply perpendicular axis theorem. So in that case, Ix plus Iy is Iz implies ICM dash plus ICM dash is ICM. So therefore, ICM dash is ICM by 2, which is nothing but mr square by 4. If you imagine another axis which is parallel to ICM dash and tangential to the disk, then in that case, let this be I2 and I2 is ICM dash plus mr square. So this will become 5 by 4 mr square. Now please tell me, do you have any doubt in this? Moment of inertia of a thin circular disk. Boys, any doubt? Sure. Right. Nana from ECL, confirmation. Right. Good. This is all about the moment of inertia of a circular disk. At different structures we will do, undoubtedly. Now imagine the moment of inertia of a square laminar. Square laminar. So which means now this is your square lamina. That is the central axis. See, for this purpose, I will do a different way. Now I'll imagine that this is Ix and this is Iy. Remember, both are passing through the same point and perpendicular to each other. And this axis, which you are calling as ICM, is my IZ. See, if I see this from this end, it is like a thin rod. This axis is like a thin rod. For thin rod about this axis, what is the formula for moment of inertia? Just now we have derived m L square by 12. This is the one which we have defined. So therefore, from this end, if I am viewing it from this side, I'll see that it is a thin rod of length A. So therefore, whether you choose Ix or whether you choose Iy, it is simply MA square by 12. So therefore, from this I can say that Iz is Ix plus Iy, which is nothing but MA square by 6. That's the deal. MA square by 6. Suppose if you want to deal something else again, this will be Iz for me. Apply perpendicular axis theorem again. Ix plus Iy is Iz. Ix, you can take it like a rod, free end. Or in this case, Ix, Iy becomes MA square by 3. Or if you see this, the end will behave like this rod, and this is the axis. This is the distance A. Through an end, passing through an end perpendicular to the length of the rod, you have MA square by 3. No, you are not believing me. Here, M square by 3. So therefore, I'm just using that. So in that case, Iz is MA square by 3 plus MA square by 3, 2MA square by 3. Right. And one more important observation is that for this square, it is passing through the center. So I want the moment of inertia about diagonal. Simple. Now you choose this as your Ix. You choose this line as IY and an axis passing through the center of the plate as IZ. Then IX plus IY is IZ. Same. But we know 2 times I diagonal is a IZ. IZ is MA square by 6. Just now we have derived. So therefore, I diagonal is MA square by 12. అదే డయాగ్రామ్ కొట్టేలా అది ఐడియా ఉందిగా మీకు నెక్స్ట్ అండ్ వన్ మోర్ స్పెషల్ ఫీచర్ ఆఫ్ ద స్క్వేర్ ఈజ్ one more special feature of the square is now for example you have this I diagonal. I am taking another axis. Theta. I. Remember, for square, I is the same as I diagonal. Why? You choose now this as Ix. A 90 degrees line, you will choose it as Ix. Again, the same concept. Ix plus Iy is equal to Iz. But this is applicable only for square plate. And number two, there the axes are in the plane of the axis is in the plane of the square. Right. Regarding square, give me clarity. Have you understood about the center, about the edge, about the diagonal, and a random axis? 4 different cases I have thought. Now tell me, have you understood this? Any doubt? ఒరే మీరు వచ్చిన వాళ్ళు మీకు ఏమైనా డౌట్ ఉంటే అడగండి అంతేగాని అడిగితే బాగోదు అట ఏమనుకోవద్దు నీకు అర్థం అవుతున్నాయని నేను ఫాస్ట్గా చెప్తున్నాను నిజంగా చెప్పు అదే రైట్ నెక్స్ట్ నువ్వు చివరమ్మాయి నిజంగా ఫాలో అవుతున్నావా రైట్ దిస్ ఈజ్ అబౌట్ ద స్క్వేర్ ప్లేట్ రైట్ నౌ యూ విల్ టేక్ అబౌట్ అరే టైం ఎంత అనుకున్నాం మనం 9:40 రైట్ నౌ వీ విల్ టేక్ అబౌట్ a rectangular plate. ECL students, give me confirmation about the square plate. About the square plate. Right, thank you. Now about the rectangular plate. This is a rectangular plate. You are seeing this in a 3-dimensional view. To my best of knowledge, I have tried my level best to draw this as a 3D structure. This is the rectangular plate. A, B, C, D is a rectangular plate. AB is equal to BC is equal to A. AB is equal to DC is equal to A. AD is equal to BC is equal to B. You can call this as length and you can call this as breadth. Right. Now, if you ask me about an axis passing through AD as some I1, and if you want to find about an axis passing through the center as I2, and if you want to find about this axis, let this be I3. So I have no time to explain all this, you know. You, from this end, you will see the rod instead of side A, you will see length A. So what about I1? Tell me. It is MA square by 3. What about I2? MA square by 12. What about I3? MB square by 12. Yes or no? Why? When you see this from this end, you will see it like a rod of length D. Right. And again, about this axis, let this be I4. Can you please help me in writing I4? MB square by 3. Now, moment of inertia about an axis passing through A. Moment of inertia about an axis passing through A. Perpendicular axis there. This is nothing but I4 plus I1. MA square by 3 plus MB square by 3. Similarly, this is O. If someone asks me IO perpendicular, this is I2 plus I3. This is nothing but MA square by 12 plus MB square by 12. That's the rectangular plate. Any doubt? Clear? Next. Next is now we require to derive moment of inertia of volume areas, but I'll just take a break. Yes, I've just introduced different moment of, you know what is moment of inertia now. I will derive moment of inertia of different structures again, but before that, I just want to express something about the torque part. So see, అసలు moment of inertia తెలియకుండా torque part define చేయకూడదు. So that is the reason why I have given a list of areas where moment of inertia term is just exposed to you. Right. Now I am defining torque again. What all I am teaching as theory is like two different paras bus. Application is vast. Right. So that is the reason why I'll take small breaks, some area. I have introduced I have introduced some basic areas. I'm taking a break. I'm just going to torque equation. Torque equation. See, for example, you choose some this is some rigid body. For example, now you choose some point P in this. Now, I'm taking a fixed axis here. Let AB be some fixed axis. And you know very clearly this is rotating in a circular path, radius r. See, I can see two things at P. Point P will have Anvit Nedravotara. Point P will have centripetal acceleration. Point P will have tangential acceleration also. Why? Because I am noticing that the speed of P is increasing. Omega changing. Alpha exists. Now, if you ask me the tangential force in this case, the tangential force in this case, I will write MAT. It is nothing but MR alpha. MAT, AT is nothing but MR alpha. That is the tangential force. See the tangential, okay, a radial force is MAC mv square by R. Now the torque of radial force is always 0. Why? I said the torque of radial force is always 0. Varun, why? Yes. In fact, the radial force will intercept the axis of rotation. So therefore, it will not contribute any torque. Okay. What about the torque of tangential force? It is simply MR alpha into R, because you know, right, this can be written as MR square alpha. Simply. So only for one particle system like that, you will simply write that torque is MR square alpha. If n particle system exists, you will write torque as sigma I mi Ri square alpha, and this is I alpha. I alpha. So which is analogous? No, what is the cause of angular acceleration? Torque. What is the cause of acceleration? Force. Force is the cause for the acceleration. Torque is the cause for angular acceleration. It is like your F is equal to ma. Right. Now, also you can write another way. Torque, net torque is sigma I Ri bar cross Fi bar. Here, when I am writing Fi bar for a system, if I am writing Fi bar, when I am writing Fi bar, it is the resultant force. You should carefully observe this line. I am speaking again. Fi bar on a particle represents the resultant force on the ith particle. Okay. And this is again, it consists of forces exerted by other particles plus force externally. Because the point which you are speaking about may be acted upon by an internal force, may be acted upon by internal force along with external force also. Suppose if a rod is held horizontally and released, weight of the torque is responsible for alpha. But for an element on the rod, it may experience force due to its surrounding particles also, like what you call as a tension. Now the question is, I'll modify the equation like this. The net torque can be written as Ri bar cross sigma of J not equal to I, because the particle cannot exert force on its own. A jth particle will exert force on ith particle. That is called Fij bar plus sigma Fi, and this is external force completely. Right. See, the problem is if ith particle exert force on J, we will call as F. Ith particle exerting force on J, we will call it as Ji. If jth particle exert force on I, we will call it as Fij, but they are internal forces. Action plus reaction is 0. Right. Now also, if ith particle experience a force like this, ith particle exert on J kada, jth particle on I. But remember, the direction of this and the direction of this are the same. Because their action-reaction pair, both are along same direction. Both are parallel or anti-parallel. So what happens in that case? 0. Cross product will be 0. For example, to take a system axis A, B, like for example, you have an axis like this, and you have A, you have B. See, the direction of force is in this direction, and Ri minus Rj is also in the same direction. Now, what happens to the cross product? 0. So finally, to conclude, we can say that simply torque due to external force is I alpha.
I found this on the web.
If whenever we are raising tau is equal to I alpha, we are speaking about the net torque external. The net external torque. And number 2, some important observation is, బాగా గుర్తుపెట్టుకోవాలి ఈ పాయింట్ ఇప్పుడు నేను చెప్పేది. The torque and moment of inertia. The torque and moment of inertia are both taken about same axis. That is the first point. Now tau is equal to I alpha is similar to, it is similar to F is equal to MA. And next, since I depends on the choice of the, because I told you at the beginning only, moment of inertia depends on the axis of rotation. The axis of rotation. So therefore, since the moment of inertia depends on the axis of rotation, so therefore, same is with the torque. It also depends on the selection of axis of rotation. And remember, tau is equal to I alpha is not an independent, so not an independent rule of nature. Right. It is derived from ಏನು ಬಂಡಿ ಮಾರ್ಚಲ್ಲ right. It is derived from more basic Newton's laws of motion. Sometimes the same equation is also called as Newton's second law in rotation. That's all. But tell me, do you have any doubt in this? The entire week, this is the theory which I'm going to use. Trust me. Why? Because the syllabus what you had is this. Moment of inertia, parallel and perpendicular axis theorem, rotation of rigid bodies, okay, rotation of rigid bodies about a fixed axis, derivation of tau is equal to I alpha, and applications of tau is equal to I alpha, only fixed axis. This is what we have for this week. So basic theory I have done, but remember the application part is too vast. So the application part comprises of deriving different moment of inertias, applying torque equations to different structures also. So now I'll go back to moment of inertia terms, or I'll simply apply one simple application of torque equation, like a very simple application. Now imagine you have a thin rod like this. Now it is held at rest by joining a string at this point. So initially at rest. Now you have cut the string at this point. Immediately after cutting, now try to see what is happening over here. You have mg here. Normal reaction here. ACM here. Angular rotation alpha here. Now the question is mg times L by 2 is the torque. How? Force arm. And this is equal to, now this is a fixed axis system. You are allowed to apply torque equation. Torque equation is allowed to apply about axis of rotation. I alpha. Tau is I alpha. And m GL by 2 is moment of inertia is ml square by 3 alpha. So cancel m, cancel L. So alpha is 3g by 2l. And let this be equation 1. This will become 3g by 4. You know why it is L by 2 alpha? ACM is L by 2 alpha. Yes or no? A is equal to R alpha. R stands for L by 2. మరి అలా ఉంటుంది. మీరు ఇప్పుడు ఆ వీక్ అయిపోయింది, మర్చిపోయారు. ఏమి ఫాలో అప్ ఉంటుంది ఇందులో చెప్పండి ఒకసారి. మర్చిపోకూడదు కదా. రైట్. అండ్ నాట్ ఓన్లీ దట్, యూ హ్యావ్ ACM. సో mg minus ny is MACM. mg minus ny is m3z by 4. So ny is mg by 4. Okay, this comes under the application of torque equation. I just taught you the very fundamental thing. Now I'll go back again to moment of inertia. Some derivations are left. I'll finish off today. Maximum derivations I'll finish off today. Right. See, exclusive cases I will add later on. So fundamental, if it is done, it will allow you to do some work. Right. Next. Yes, ECL students, do you have any doubt on this part which I have done? Torque equation part. Right. Thank you. Students, see, if a time end, అరే ఒక్కసారి Dakshesh, can you please talk to me? Thin spherical shell. I'm just giving basics. Thin spherical shell. Now we have a thin spherical shell like this. And this is the axis of rotation. Right. About this diametrical axis, I want moment of inertia. For this purpose, I will imagine a portion like this. center, d theta. Agreed? Now I can see a ring now here. Now here also this is this is not volume distribution. This is again a surface distribution. Why? Nothing is there inside, thin spherical shell. So sigma refers to mass per unit area, which is given as capital M by 4 pi r square. Sigma refers to mass per unit area. Now you can see there is a ring over here. What is the mass of elemental ring? Mass of elemental ring is equal to sigma, 1 minute. Width is r d theta. Okay. Perimeter is 2 pi radius of this part, which is nothing but what is the radius of this part? Here small r is r cos theta. So r cos theta. Hello, this is only mass. 2 pi sigma r square cos theta d theta. That is the mass of the element. So moment of inertia of elemental ring. Whatever it is, that is, if you take this as small m dash, I will write this as m dash. What is the moment of inertia of ring? mr square. M dash radius is r cos theta square. M dash r cos theta square. Any doubts? Boys? అరే ఇప్పుడు ఇది కదా రేడియస్ కదా, అప్పుడు ఇది ఏమవుతుంది? ఆర్ కాస్ తీటానా ఆర్ సైన్ తీటానా? అడ్జసెంట్ సైడ్ కదా, ఇది కదా మీకు కావాల్సింది రేడియస్, రేడియస్ ఆఫ్ ద రింగ్. అండ్ టెల్ మీ, ఈజ్ ఇట్ క్యాపిటల్ ఆర్ కాస్ తీటా ఆర్ క్యాపిటల్ ఆర్ సైన్ తీటా? ఒరే ఏమిట్రా డౌట్ అడిగారు, మాట్లాడతలా, కాస్ తీటానేగా, రైట్. సో దేర్ ఫార్ moment of inertia is integral, a moment of inertia, total moment of inertia, I is integral 2 pi sigma r square cos theta d theta. This is mass term. Radius term ఇప్పుడు వేస్తున్నా, r cos theta square. ఇప్పుడు ఇందులో 2 pi sigma r square r power 4 బయటికి ఇంకేమొచ్చింది? వాట్ ఈస్ దేర్? కాస్ క్యూబ్ థీటా డి థీటా, రైట్. లిమిట్స్ దేనికి దేనికి ఇంటిగ్రేట్ చేస్తారు మీరు? -π/2 టు +π/2. నాకు కాస్ క్యూబ్ థీటాని 3 థీటాల్లో రాసుకోవటం మీకు వచ్చు కదా, నాకు చెప్తారా? వాట్ ఈస్ దట్ రిలేషన్? కాస్ క్యూబ్ థీటా ఈస్ రేటర్, అలా చూస్తారు, రాదా మీకు? బ్రహ్మాండంగా ఉన్నారు. cos 3 theta plus 3 cos theta by 4. Actually, you know the relation for cos 3 theta. Cos 3 theta is 4 cos cube theta minus 3 cos theta. So this you will write it as 2 pi sigma r power 4 by 4 integral cos 3 theta plus 3 cos theta d theta. Limits are from minus pi by 2 to plus pi by 2. See, by doing the substitution, finally you will get the moment of inertia as 2 by 3 mr square. Remember, this is about a diameter. This is about a diameter, which means the moment of inertia of the thin shell about a diameter is simply 2 by 3 mr square. What if I ask you about something like this, a tangent like this? This is ICM and this is I. So I is ICM plus mr square. 5 by 3 mr square. Any doubts? Next. Moment of inertia of a thin spherical shell. Solid sphere. Now you have a solid sphere like this. Whose moment of inertia is like this. Whose moment of inertia is like this. Next. Right. So that is the moment of inertia of a thin solid sphere. Sorry. Oh, solid sphere, complete, full volume. So because this is a volume element, you are not supposed to use, now you should use a rho. Rho is called mass per unit volume, which is given by m by 4 by 3 pi r cube. Remember, uniform. This is uniform. Otherwise, you are not allowed to use that. Now, I think you got the point now. What I am going to do is some shells. You imagine it like an onion and shell over shell, shell over shell, shell over shell. Right. Now you have a shell of radius r, thickness dr. So what is the mass of the elemental shell? What is the mass of the elemental shell? Tell me. The mass of the elemental shell is, what is the volume? 4 pi r square dr rho. If you have any doubts, ask me now. ఇప్పుడు తప్పు ఎక్కడ జరుగుతుందో నేను చాలాసార్లు చెప్పాను మీకు. ఎప్పుడు జరుగుతుంది? ఇలాంటి పాయింట్స్ దాటేస్తారు. రేపు మీరు అప్లై చేసేటప్పుడు రాదు. ఫర్ ఎగ్జాంపుల్ రో నాన్ యూనిఫార్మ్ ఇస్తే ఇప్పుడు నేను చేసే ఫార్ములా కరెక్ట్ కాదు, మీరు ఇలా డెరైవ్ చేసుకోవాలి. రైట్, మాస్ ఆఫ్ ద ఎలిమెంటల్ షెల్, మూమెంట్ ఆఫ్ ఇనర్షియా ఆఫ్ ఎలిమెంటల్ షెల్. వాట్ ఈస్ ద ఫార్ములా ఫర్ మూమెంట్ ఆఫ్ ఇనర్షియా ఆఫ్ ద ఎలిమెంటల్ షెల్? 2/3 times mass radius square. So 2/3 times 4 pi r square dr rho into r square. This is 8/3 pi r cube rho dr. కరెక్టేనా? ఇంకేమైనా ఉందా నాకు? 8/3 4 r power 4, రైట్, r power 4, రైట్. Now total moment of inertia of sphere is integral 8/3 pi r power 4 rho dr. So this is from 0 to capital R. This will be 8/3 pi r cube, pi r power 5 actually. Pi r power 5 by 5 times density. కరెక్టేనా? అంతేగా ఇంకా. ఇప్పుడు దీనిలో యూ కెన్ రైట్ దిస్ 2/5 times 4/3 pi r cube rho times r square. కరెక్టేనా కాదా? Why? Because I know that this is the mass of this sphere. 2/5 mr square. This is the expression for moment of inertia of the sphere, a solid sphere. Similarly, you will derive for moment of inertia of cylinder also. Moment of inertia of a solid cylinder. Solid cylinder. Moment of inertia of a solid cylinder. Very simple. It's like a disk for me. It's like a disk. About this axis, it is like a disk for me. Simply mr square by 2. Suppose if they ask you about this point, simple. If it is a rod, I would have written ml square by. If it is a rod, I would have written ml square by 12. If it is a disk, I would have written mr square by 4. But seems to be like both. So therefore, you will have ml square by 12 plus mr square by 4. That is moment of inertia of a solid cylinder. Any doubts, boys? What else we have? So I am giving just only basic cases.